you.
Thank you, Caroline. Many of you know me. I'm Jagannath. I'm a lecturer here, GIS and surveying I teach. Today I'm going to talk about GEOBIA or GEOBIA in Europe, people call that, which is Geographic Object-Based Image Analysis, and I would like to welcome you all in today's talk. Basically, I will talk about the concepts, how it was evolved, and what are the fundamental principles behind it, and the application areas, and the projects that I worked with in different areas, and the challenges I faced when I worked in the different projects, and the future outlook I will be presenting. So in outline, for example, how we perceive, realize and interpret objects, and what are the objects as such, and what are the geographical objects. I'll be talking that. And when we talk about object, we need to talk about pattern recognition, how we recognize any patterns, how we know a car is car, a tree is tree, and how we know group of trees and many cars. And in this data intensive era, we have ultra high to very high resolution satellite images. By saying that, we have from drone to satellite, from kilometer to centimeter accuracy images we have. And I will be talking about geographical objects and hierarchy, how we can perceive the objects in different hierarchy. So can we perceive in topological relationship, that is neighborhood, or can we perceive in vertical component or in hierarchy? And the topic itself is related to scaling and multi-scaling issues, and why we need to consider multi-scaling. For example, can we perceive everything in one scale or not? We can't perceive everything in one scale. As I said, a single tree, group of trees, and eventually plantation and a forest stand, we can perceive that easily in our head. So how we can automate that in the human-computer interaction environment, that's the challenge, and all the research is focusing on that. And where it can be applied and who will benefit, I will be listing some of the areas who can benefit and how we can apply. And available software, open source as well as commercial, I'll be talking that, and I will conclude with a positive note. So let's have some examples of pattern recognition, how you recognize this. This is Olympic symbol, and you can perceive easily this as 5 circles and not 9 different shapes. But if you go deeper, you can say, okay, there are 9 shapes different. But what we do as a human being is we try to tend as simple as possible, we try to perceive. That is law of simplicity. But if we want to go deeper, we can go for the complex as well. Similarly here, in this example, all the rows have a similar structure, but we visualize columns of squares and circles. If you look in a row, you can see square, circle, square, circle like that, horizontally. But we tend to see vertical at first instance. That is the grouping of similar objects. This is law of similarity. Similarly, in recognizing the patterns, here in the marked in red are perceived as faces, but these are not human face. These are forest or some natural features. So what we do is we tend to patronize the familiar thing. It's because we know human beings than other. So this shows that the patterns are important in objectification. So when we use pattern, example here, you can see, a zebra here. So according to the context, for example, if this is in room, we say this is a chair with zebra pattern. So some knowledge will guide us, okay, where we are, what is the context. And similarly here, the contrast black and white and form, where black line on white background. So these all are the patterns. The color, form and arrangement evoke certain patterns, that is for our knowledge. And we experience regardless of scale. What scale we are looking, it doesn't matter. So with this background of pattern, let me introduce with the data era now. We have remote sensing images, we have GIS data, open source data, every data are available. You can go to Google Earth, Google Image and get all the data. We have to pay some of the data, we can have free data. So having said that, we have different sources of data. So let's say a remote sensing image, we have UAVs, we have airborne and we have terrestrial as well, from land surveying to satellite imagery. So we all capture the data and we analyze. So we have big data, that is we have lots of data. And we are in a dilemma, what data I want to use and how I want to model and how to use this data or those data, how I can do that. And we have user community. So there are challenges. So what data I'm going to use and what data is out there and how to organize big spatial data. How to get the data I need. For example, I have MODIS image, I have Iconus image, I have QuickBird image, I have GeoEyes now, and I have WorldView 3, different types of satellite images. What image I should choose? I have different open source data, like OpenStreetMap to other open source data. So how I go to that particular data for my application, for my research question. So these are the challenges we are facing nowadays. And we have to figure out how to do that and how to model big data and how to access and use the big data for our research question, for our application. So you can see in this is a very high resolution aerial photograph. You can see different objects, geographical objects that I scribble here. Actually, you can see this is grassland. From land use perspective, this is oval or playground. From land cover, this is grass. And here you can see trees or group of trees. Similarly, a polygon here I extracted as a representative one that I will be presenting more in later. The idea of showing this is very high resolution aerial photo, different geographical objects we can perceive, we can delineate. And this is local image. So how we can perceive that in multi-scaling or in different level. For example, if you focus on that particular red polygon here, and if we segment this into different levels, then it will disintegrate. You can see here this is single one and this changes to 3, more than 310 or more than that. And here you can see same polygon how it is disintegrating. So now you can figure out, okay, if I go with this level, I might be interested in single tree. And here you might be interested in a group of trees or plantation. So you can see this as a group of trees and this as single tree. But there are lots of noise, right? That's not perfect delineation. So we have to we have to use our knowledge. So we can't 100% rely on the software. We can use our knowledge, the context-based knowledge, to refine the segments or to refine the image objects. So you can see in this one how we perceive the real world objects in different hierarchy and what is the relationship of same object to the sub-object and super-object. So here in the left one, the white arrow shows neighborhood relationship, that is the topological relationship, or in other words, horizontal relationship, like in horizontal working environment. So same level relationship. The black arrow shows the hierarchical relationship or vertical relationship, that is with the sub-objects and super-objects of the same object. So here, if you think of this polygon, it is disintegrated into many here, and it has a relation with all these disintegrated part. Similarly, this one here further disintegrate into many objects. So when we define or recognize the objects, we look into shape, size, color, texture, form. These are the characteristics. Every object inherits these characters. And we realize these characters by perceiving, by recognizing, by interpreting. That is, I interpret differently than you interpret differently than Mr. A or B, which is subjective. But when we do the analysis part, then we do objective. We have some rules and we follow those rules. So this is, as I said earlier, each object knows its neighbor objects, which is a topological relation or horizontal relation. So for example, this central object knows its neighboring objects, and its sub-objects, which is down below, and the super object, the source where this object is coming from. So this concept started, actually segmentation is not new. It was in 70s it was started, but for the remote sensing community, the object-based image analysis approach came into more practice in 2000, and after that it is widely used, and it is now a new paradigm, and people are using in different application areas. And the benefit of this is not only remote sensing, not only GIS, it integrates both. So we have data, remote sensing data or aerial photo, we extract the information and we develop the knowledge in GI environment or geographical information environment. And the modeling is possible as well for the scale-specific ecological processes through multi-scale representation. For example, if you want to study some ecological application, let's say backyard garden or front garden or urban trees, and then that can be studied using object-based image analysis. If we can map the gardens, I will come back to you that later. If we can map the gardens, these are the resources for wildlife, these are the resources for spatial ecological analysis. So the concept of scale and object hierarchies, how we make different hierarchy. If just let me go back here. Sorry. On this one. So this is the main concept here, how we make or how we hypothesize different levels or hierarchy. So let's say L is, I don't want to make it abstract, so just think about three different L minus 1 and L plus 1, three different levels. So L is one level and lower level and upper level, three different levels, and we can categorize all these segments or objects into different levels. For example, here N plus 1 is higher level, you can see just two objects or two segments, and in N you can see 1, 2, 3, 4, and if you go further down you can see 1, 2, 3, 4, 5, 6, 7, that is lower level. So when we go further detail, that is if we go to pixel level, we have many objects if you think pixel as object. But when we think of an object, what we do is we merge the contiguous homogeneous pixels. For example, when you want to define a car or a tree, you are not after a single pixel, you are after a car. to form a car in any image or in any photo, what you do is you merge similar pixels that define a car, that define a tree. So this shows that we have different levels of hierarchy. So can we achieve this with per pixel approach? Can we analyze this object thing by pixel? So when we say pixel, this is a picture element, that how much it is showing in the ground. For example, if we say 1 meter spatial resolution, that is 1 meter spatial resolution means ground is represented in 1 meter pixel here. So if we want to analyze those objects, it is not possible by pixel-based approach. We can't do that, and we have to include the knowledge, where you can see here how we perceive with our cognition. There is real world, and we are perceiving like this with different objects, different orientation, different shapes, different sizes, all we can incorporate. Let's have a look at another example here. In figure 1 here, A, B, C, I'm showing A is square, which is a pixel. Here in B, different square, you can see 1, 2, 3, 4. In C, many squares you can see, right? In one square here, 2 objects are easily fitted. You can see this one and this one, 2 objects. But here, with 1 square or 1 pixel, the object is nearly fitted, right? But the case of C is completely different. For this particular object, can you see how many pixels are there? Not only 1, too many. I have to count, right? So for this one, if I have to count, then I will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pixels are representing one object in that. Here, 1 pixel and the object is similar, matching. Here, in 1 pixel, many objects are there. That means this shows that we have different resolution image data, satellite data. What is our proposed, what analysis we are doing, it depends on that, what data we are using. So if we want to analyze in this scale, in this level, then we need to go for object-based image analysis. We have to merge these pixels into one object to characterize this particular object. We can't characterize here with pixel-based approach. But here, this is, we have to go to sub-pixel. 1 pixel is not enough to characterize these objects. But here, pixel-based approach is okay. But you can see here the mixed pixel as well. So this is the problem. We have to go for object-based image analysis with the data and the question in our hand, what we are asking, what we are doing research. So why objects, not pixels? As I said earlier, some image data shows differently than others because of the resolution. Spatial resolution, spectral resolution, and radiometric resolution. Different resolution we have. When we capture the data, we define these resolutions. So here, this is an image showing Landsat TM data of the same area. If I show with the iconous image, it will be like that. So the difference you can visualize with 2 different images for the same area. So per pixel approach is spectral information only, and it is not that powerful. And per pixel approach less efficient when targets are smaller than image resolution. And the GEOBIA, our object-based image analysis, where we consider spectral as well as spatial information. When we say spatial, we are talking about shape, texture, size, and context. So here, if I want to go for analyzing trees or houses, then I will go for object-based image analysis. The characteristics are here. The parameters we have available in object-based image analysis, for example, color information. We have color statistics, we have size, we have shape, we have neighborhood information, we have hierarchical information, and we have sensory-specific information. So from this table you can see that object-based image analysis is more powerful than pixel-based image analysis because of these extra available parameters. That's why we go for objects, not pixels. A simple example here, beyond spectral dimension, an easy case. How you distinguish, this is water body, you know that straight away. How you distinguish pond, river and lake. So is this river or pond or lake? So for that what you do is you automatically use the context. Use your knowledge. Okay, this is close to house, close to residential area. The house is there and meadow is there, transportation is there, road is there, and trees are there, and the water body is there. And then what is this water body? Right? So you can use your knowledge. Similarly, the context. In this example here, the alphabets H and A have the same shape but are understood differently based on the context. We easily say the cat. And similarly, this is before it was, we don't know, no clue what it is. When I put fork and knife, and we know that this is plate. So that's the context. So GEOBIA is context-based. So when we say GEOBIA or object-based image analysis, we always talk about the context. And it uses the color, shape, texture, and size of object, as well as their context and relationship in multi-scale environment, how they are related in multi-scaling. And it uses all the semantics like we do as a human being. And image object is a result of, as I said, contiguous homogeneous pixels. That is, we merge the similar pixels and we define an object. It is emerging subdiscipline of GI science, and how it is possible is the trends of two things went together, that is the advent of very high resolution imagery in 2000 and the availability of powerful off-the-shelf software e-cognition in 2000. So that's why it came into application and practice. And it is iterative, so we do segmentation first and then we classify. But we don't stop on that. What we use is the knowledge from classification is again used for segmentation. It is in iteration. I'll show you an example. So first we segment and then we classify. So let's say we have 1, 2, 3, 4, 5 different classes. And again, what we do is we make a segment in this particular strata because we use the knowledge. And again, we make a reclassification, so which is more accurate. And we merge, and finally we come up with a map. So that is the principle that we apply in simple saying in GEOBIA. So let me sum up the philosophy here now. So very high resolution and ultra high resolution images, they have wealth of information. So we have all the information in those images that we need to tap and develop knowledge, right? So we need to tap the meaningful information from where we can develop the knowledge. And object perception and delineation is main fundamental here. And we might think, it's a technique for more maps? Is GEOBIA a technique for making more maps? No. This is data intensive GIS area, and it is not about more maps. We need new methods and new technology to capture the changes in spatio-temporal things. So this is one of the new method evolved that reflect our cognition. So how it works, the workflow is first we have image. You just can follow in the left, and we do the segments that I said earlier, and then we make objectification. We have objects as candidate objects, and we classify in abstract, and we refine the objects, and we make another classification. Again, in iteration, we do the classification by using our knowledge. We add the context-based knowledge, and we refine. At the end, we will achieve our targeted classification result. And the principle of iterative workflow is explained here. So we have this image object hierarchy, and this is evaluated by domain expert knowledge, where we use our semantics, spatial semantics as well as thematic semantics. And then domain expert knowledge is made explicit by ontology. So this is the area that at the moment the focus is there. And this ontology is basis for rule set. At the end, what we do is we develop rule set and we train the software to work according to our rule set, and we'll have the end product. And the rule set creates image object hierarchy. So this is in iteration as well. The important message here is, okay, we have to develop rule set that will help the software to train and give us result. So object-based classification is we have sample-based as well as rule-based, two different. So in the sample-based, what we do is we need training samples, that we select the representative training samples. If we have classes, let's say vegetation, no vegetation, trees, road, building, what we do is we collect 10, 15, depending on the area, representative samples, and we train the rest of the segments. And in the rule-based classification, we apply fuzzy membership function based on expert knowledge, and then we refine using the nearest neighbor classification as well. That is possible. So that's the background, what is GEOBIA and what is the concept. Now, from my experience, that I worked in different projects with the application of GEOBIA that I'm going to show now. Any questions so far? Boring? If you have any questions, just interrupt anytime. So I will be presenting now the application of GEOBIA in large-scale vegetation communities mapping, backyard garden mapping, and vegetation patch analysis, spatial object recognition, and how we associate the object recognition in GEOBIA from software-generated product and the mental mapping product, when we give human being how they scribble the map, their surroundings, and how we can get those products from the software, and we compare that as well. And ongoing collaborative works, I will be talking here, native grassland mapping that one of the students is working on, and urban tree change depiction that I'm working, and a robustness index in segmentation and classification, and ontological knowledge-based modeling I'll be talking briefly. So this is from New Zealand, vegetation communities mapping in Dunedin. So many of you know it is in South Island, in University of Otago when I was there. And as I said, we have original image, we have first segmentation, and then we have classified image. This is the simple two-step process, segmentation and classification. So we have different scale in segmenting, that is scale parameter. It's an abstract term, but you can think of as a fine resolution and coarse resolution. So if we go further up, what we get is we get bigger size object. So you can see here how they are merging to make bigger and bigger. So for example, if I go here and further here, you can just focus on one area and how it is merging. So this shows that, okay, we might be interested to pick up, let's say, a road in one scale, but houses in another scale. As a human being, we easily figure that house in very fine scale, but roads in bit coarser scale. Like here in the segmentation we can do in the software environment. So what we did first is we differentiate urban and suburban stratification, and then we use segmentation scale to do that, and with a bit of manual aid we refine the boundary of strata, and we have industrial, residential, vegetation and water. For example, you can see here the coast, and close to the coast industrial area, and close to that residential, and bit far away vegetation from the city. The CBD area is this, where you can see the industrial as well as residential, but close to harbor is industrial, which is obvious. And once we have this strata, then we further classify within that. For example, vegetation strata, then we can go for grassland, shrub, exotic shrub, native shrub, scrub, like that, different vegetation types, trees. And in residential, we went for garden and houses. And in the industrial, tree group and amenity pasture. And we define with some rules, with some area. For example, if we say tree group, how much is the area we should go for tree group? For example, let's say less than 1 hectare or more than 1 hectare, like that. Residential, garden and amenity pasture, and in vegetation strata, vegetation patches greater than 0.8 hectare, forest, plantation, pasture, etc. And at the end, we ended up validated the map and produced this map, where we have amenity grassland, pasture grassland, rough grassland, dune grassland, garden, etc. So this is useful for people who are working on spatial ecology, who are working on wildlife. Yep.
So did you identify that just from the thermal images, spectral analysis, or did you do some ground truthing as well as to each pixel was?
We went to the field for ground truthing, not from the image only. And we developed the accuracy metrics, and we reported the errors and accuracy, everything. You can't rely on just on the image. You have to ground truth, you have to validate. And that's the one bit of the project. The other bit is backyard garden mapping. So these large vegetation and biodiversity resources in private gardens of cities, and very few studies because of the access problem, people's private property, and there are no appropriate methods on that. And garden patches were mapped, not individual gardens, and because these are the resources for birds, foraging, and many other wildlife, people's backyard. And the methodology we adopted is we have image, we orthorectified the image, and we did segmentation in level 1, and we did another segmentation in level 2 to extract the private gardens, and we classified the water, vegetation, industrial, as I showed before, and we have training objects from large scale aerial photographs, and then we classify with the training objects. For garden 1, garden 2, garden 3, we define this based on the density of the vegetation in the backyard. How we define garden 1, garden 2, garden 3, I'll show you in a minute. And later we did the accuracy assessment with 35 validation blocks, which are 120 meter by 120 meter.
Could you have not done that using property boundary or leasehold?
Yep, that I'm using in Hobart at the moment. I'll show you in a minute. So this is how we define the density of gardens. You can see here, this is with the near infrared and multispectral image. And this is panchromatic. When we merge this, and we can see a bit more detail. And the garden one, you can see here, bit denser. Garden 2 is not dense, and garden 3 is kind of open space. But it's not open, there are houses, but still you can see the density of trees. You can feel from 1 to 2 to 3. So dense trees, and open grass. And the accuracy of the classification was assessed with 120 meter random square, and the relationship was reported. So, for example, if there is one botanical garden with having very big area, less than 10,000 meters square, then you can see here this is number of garden, which is just looks like 2, but the area is so big. And 2 int, you can see the first one here, and the number of gardens in size. Very little patchy gardens are there too. And at the end, the density map, percentage gardens in relation to built up area was prepared and reported. You can see here in the industrial area, no gardens, and in the hills, highly dense gardens, or the people who are living in the hills, they have dense gardens. But in the industrial area and in the CBD, no gardens, or very less, 19 to 39%. And that's the GEOBIA approach I used. And the other one I used, GEOBIA, for methodological approach in assessment of vegetation patches in diverse geographical territories. So from 3 different countries with the Landsat data. So I downloaded and analyzed the Landsat data from Christchurch city, where I lived for certain years, and then from Nepal. So these all are vegetation areas, that's why vegetation patches. This is a national park, more homogeneous vegetation along steep hills, and protected area, no residential areas. And from Mount Ventoux in the south of France, which is also vegetation area, great diversity of flora and fauna close to peri-urban environments. The 3 different areas were chosen, and the methodology was adopted to create the hierarchical framework of decomposable image objects. 5 levels in hierarchy. For example, this is a representative one from New Zealand. I'm not showing for all how it is merging, just to show in a simple case. If you go with this boundary red one and go back, you can see how it is disintegrated like that, further like that. So you can see now here it is picking up the textures and the density. And the indices were used in developing the model. We can have this object information in the software system, where the gray level co-occurrence matrix was used. NDVI is normalized density vegetation index, which is a ratio between 2 bands, infrared and red, was used. Asymmetry is a geometry, which is a geometrical feature of object. Density is also a geometric feature, and shape index is also a geometric feature. These were used, and the aggregation and disaggregation were visualized. You can see here, these are 3 or 5 different, 1, 2, 3, 4, 5 different levels, and how they aggregate in a cursor level. And this can't be seen, sorry. And the indices were computed using a simple statistical approach, where we use the relative interquartile range The reason of using this was it is considered more robust than medians. And we measure the variability of appropriate scale. What scale would be appropriate? This was in 2012, and later there is another development I will be showing you soon. We can estimate the scale now with the local variance, and we can tentatively predict for this area, for this object specific region, we can have this scale or this segmentation label. And we are trying to optimize the scale, where we were minimizing the variability within the scale, and we were maximizing the variability across the scale. So if we are considering one scale, we try to minimize the variability, but if we are thinking of many scales, then what we do is we maximize the variability to define the optimal scale. And the other example we recently published, and it is a software product and the mental mapping comparison. How the people can go. This is from Mount Ventoux and from France when I was there. And we focus on color and texture. So basically, we make segments giving the weight to color and giving the weight to texture, and we develop segmented maps, and we gave those to human subjects and asked them, can you please delineate in your way whether the software generated products are matching your thinking or not. That's the whole idea in this project. And we collated the results, and the protocol at 2 stages we done, mental mapping as well as segmented image, stage 1 and stage 2. The human subjects were chosen to address the effect of prior knowledge in spatial object recognition. For example, 4 geographers, 2 ecologists, 2 economists, and 2 computer scientists, and the children of 12 years were represented there. And we asked to identify and characterize several land usage and land covers. So we asked them from small houses to forest and grassland. So this is a representative result for stage 1 of the experiment. The ecologist, when we give it to him, what he did is he scribbled grassland and bare patches of grassland, shrubs, unsurfaced road, and coniferous trees. So this is land use he did. So here a representative result for stage 2 of the experiment, and here you can see the red dots for house age. So later we collated all the results and we plotted, and some of the examples I'm showing here. The human subjects, most of them agree on same or close scale. For example, for camping, most of them agree, 6 of them in one scale. In rocky ravines, most of them agreed. For area type, land cover, land use, and they were preferring higher scale, that is coarser scale. So here, for housing area, most of them were saying, okay, this is more than 250 scale. And ski area as well, 5 people were saying that. And the degradation of distribution shape was there. And grassland is interspersed by many copses. That's why here you can see people are different in their thinking for grassland and forest. And forest patches are not homogeneous as well in the region. And the color versus texture, we analyzed that, and most of the human subjects consider texture for large area type classes. For example, forest and rocky ravines. But for other classes, color has preference. So here, this is for texture. And the limitation of that is tight sample. We can't generalize from that. We have to have representative sample, just 10 or 12 people can't be generalized. But still that shows some indication. And we analyze the comments. We rank the comments in main 4 arguments by color, shape, texture, and confidence. So how confident are they? And what are the color characteristics? What are the shape characteristics and texture for different land cover and land use? And we analyze the association between object recognition and pertinent scale. Object specific scales are there. For example, for forest, people prefer high level classes. For houses, they are preferring fine resolution or fine classes, which is obvious, but that's the proof. So with all this, I have some challenges I faced and I would like to share with you. So the challenges in different projects were recognition of objects and their objectification for context. For example, classification scheme of vegetation communities. I mean, there is subjectivity in vegetation communities classification scheme or class hierarchy. When we have classification scheme from ecologists, what we do is we translate that to class hierarchy in computer system and we implement that. The subjective thing, when we implement, we can't get perfect results. And the pertinent scale for delineation, what is the specific scale to delineate certain land cover, land use? That's the challenge. And the precise quantification of the perception of human subjects towards real world objects. How we precisely quantify our perception. That's the another challenge. And nowadays, the development is going on, but still there is a challenge of transferability of rule set. Okay, we can develop rule set in one area, but how we can transfer that to different territory? It's because trees in Hobart are different than trees in Holland or trees in France or in New Zealand, wherever, even in Melbourne maybe. So that's the challenge. And as such in GEOBIA, we have challenge like objects, how we define objects, and how we perceive shapes, how we define texture. We have different metric to define texture, but still we have challenge to measure or map accurately. And the context and pattern, similarly semantics and knowledge integration, how we can integrate the semantics and knowledge. The research topics, for example, what we are thinking at the moment, and these are challenging, the hierarchy and scale concepts. So people might think that this is abstract, but this is very simple, but difficult to communicate. Everywhere when we think of real world objects, we are thinking in different scales. New algorithms for segmentation, that is really needed. We can develop some algorithms to test the segmentation method available and to verify. And GEOBIA and change detection, how we can use the change detection over time. For example, for time series data, can we use GEOBIA? That's another topic. And optimization of segmentation procedure, how we can develop optimization routine for segmentation procedure. And the optimal segmentation scale for specific target objects. As I said, if we are interested in agricultural field only, and how we can say that this is a particular scale where we can get the agricultural field. And ongoing projects and future outlook. Here, natural grassland mapping, Bethany is working, who is a PhD student, and I'm working in collaboration with Arco Lucia. Arco is a primary supervisor of Bethany, and she's doing in Tasmanian Midlands. She's almost done the mapping, and she's looking into another problem within GEOBIA. And urban tree change mapping over time in Hobart City in collaboration with Jamie Kirkpatrick that I'm doing. And ontological modeling in GEOBIA, that I'm looking into at the moment, and spatial mapping of bushfire using GEOBIA, whether we can create some history of fire reconstruction using Landsat data that I'm looking into. And this is the work from Bethany, where she developed the native grassland mapping using Landsat data and worldview data. And you can see here different land cover classes: agriculture, woodland forest, and basically 2 native grassland community, Poa and Themada. And the manuscript is under preparation. And depicting urban tree change. And this you can see here no vegetation, that I'm defining 2 classes, very broad classes. And there I can do within no vegetation building, road, and in vegetation grass, amenity, pasture, plantation. Within plantation I can have group of trees and trees. This shows the parent-child relation. For example, if you go up here, these are the child from there. So no vegetation child are building and road, and the vegetation child are grass and plantation in one level. In another level, amenity, pasture, group of trees, and further down the track, trees. And answering your question, this is imagery overlaid with cadastral boundary or cadastral property, and we can segment using this and have a meaningful object. So we can have different objects if we use this and if we don't use this. That is, if we use the cadastral boundary, we have different objects. If we don't use cadastral boundary, we have different objects. So we segmented the imagery in fine scale with an inclusion of cadastral boundary as thematic layer, that it is possible, and it gives us more realistic objects of the real world. And the inheritance is there for the classes, and how it looks like in cursor scale. For example, if we are interested in the road, we can go with this scale. And using ontology in generating knowledge base. So this is a framework that we are working on, how we can use the ontology in generating knowledge base. So we have image, and we do the segmentation. We have image object, and we extract the features with texture, shape, and color with different sizes, and then we generate the knowledge base with semantic query. I will be explaining this further detail here. With the process model for the extracted objects. So we have in pixel level, let's say image, and then we do segmentation, we have object detection, and then further down the track we'll have first segmentation level with estimated scale parameters. We can estimate the scale parameter, the segmentation scale, and we can have the relationship of parent spatial object S1, parent spatial object S2, parent spatial object up to n, different types of objects, and then similarly for child objects. And we can have object information. How we can estimate the scale is an example here. With the local variance, we have the scale here and rate of change here. And that gives us, okay, which is the tentative or estimated scale parameter for object specific segmentation. And we are integrating the cadastral boundaries for knowledge base in the eCognition software, eCognition environment, and using the editor for open source ontology editor to refine the object and object information properties, and later we are creating the rules and making decision rules. And the future outlook in this topic is robustness index. Okay, all these analysis or applications, the robustness is always a challenging one. How we can say this is a robust one, and we always aim for that in research. And how can we conceive robustness philosophy in GEOBIA, in segmentation as well as in classification? When we do the segment, how we say that our segments are robust and good enough to further carry on. and how we can assure ourselves the classification is robust and we're happy with that, and how it can be defined for segmentation and later for contextual classification in rule set. That is challenging and we're exploring on that. The areas of direct application and benefit from this technique or system, what are the areas that can directly benefit it locally, nationally? The bushfire mapping and fire history reconstruction. For example, we have Landsat data available freely that can be used. Historical Landsat data can be used for fire history reconstruction mapping, which is topical for Australia. Agricultural field open soil patch extraction for agricultural study, and crop patch extraction for agriculture focus. So how we can extract the patches of different crops, veggies or other crops. We can do that. And forest inventory, tree crown extraction can be done, and we will be doing that with PhD students. And the software, eCognition is the main software that we use, and it's an expensive one, I would say. It's from Definiens in Germany, and now it is owned by Trimble. This spring, which is from INPE Brazil, it is open source. You can download and try. And Orefo Toolbox from France, and it is also open source. So these are image analysis or object-based image analysis software. And feature extraction in other GIS and RS is also possible in GIS and remote sensing. Like ERDAS, INVI, ArcGIS, these are not open source. These are commercial software. And the conclusions from this is object-based image analysis is a new paradigm in geographic information science. It can be used for many application areas, from agriculture, forestry, ecological applications, urbanism, urban study, and water stress mapping and monitoring. And I would like to acknowledge Thomas Plaske for some of the slides, and Didier Josselin, and Prasant Marpu from Iceland for some of the slides. Thank you for your attention.